All right, let's do that again, because what we actually described is pretty much the function of a nerve impulse or an action potential. When we look at a neuron, what a neuron does, it receives impulses from other neurons. They're either excitatory or they're inhibitory. They either tell the next, this neuron, this receiving neuron, to keep firing further or to stop and not fire the next impulse. These are graded or local potentials. They are sort of shouts of what the neuron should do. They're opinions, so to speak. There are about 1,000 of those connections that they can have, up to 1,000. Then we have an area in the neuron. When you look at the neuron, you have the cell body, you have the dendrites, and then you have one long extension called the axon that goes to the next target, which is either another neuron, a gland, or a muscle. So when we look at the area right before that axon starts, it's known as the axon hillock. And when we have all these local shouts, these impulses, these excitatory and inhibitory impulses come together there, and they sum up what's happening, and at that side, if there is enough of a change in the voltage at that level, a threshold is reached, and at that point a neuron will fire, and we have a nerve impulse that's created and moves down the axon along the axon. The axon is cell membrane surrounded, so it has that oil film surrounded with a lot of sodium and potassium channels, as well as sodium potassium pumps in them. And so when we send an action potential from that axon hillock down the axon, what happens first? We have sodium channels open, and sodiums will move into the axon from the outside right there at that local area, and they change that voltage locally from a negative 60 to about a positive 20 millivolts, because they take all that positive inward. That's known as depolarization. And then when we have enough, when we reach plus 20 millivolts more or less, or here in the picture is plus 30, so it depends a little bit, but they have a voltage switch, and when we reach that thing, that switch, it closes that channel, and so that stops the influx of sodium. At that point, we're going to have a potassium channel open. That's also a voltage gated channel. And when that opens, potassium will flow out. What that does, the potassium will carry with it a positive charge again. But now it goes from the inside of the axon to the outside, right outside. And so the inside will become more negative again, as compared to the outside, which will become a little bit more positive. So the voltage changes and the polarity becomes greater. So we call that repolarization, and we reach again more or less the resting membrane potential. A little bit more because we go a little bit deeper and more polar, because the potassium channels, they're very close to, they're slow to change, they're slow to close. But the resting membrane potential is reestablished soon after that, because sodium and potassium pumps are constantly at work, and they reestablish the chemical environment, where then again we have more sodium on the outside and less sodium on the inside, as well as more potassium on the inside and less potassium on the outside. So this is an electrochemical event. That means we move chemicals around, and with it, we pull an electricity with it, a charge, and that makes it the electrical. So that's why it's a little bit complicated. All action potentials are all equal in form, intensity, and duration. They're not graded. They just go. They're all or nothing. So if you hear something, or if you have a stimulus that needs to be an intense stimulus, you can't just send a bigger action potential, because it's just the same action potential. So what you need to do is you need to code it, and the coding is frequency. So if a stimulus frequency fires, that means it's a stronger stimulus. And we can do that because action potentials are really very, very brief. Action potentials move along the axon in a unidirectional way. They don't move backwards, because they can't. Once we run an action potential in one place, the chemicals are messed up. We cannot work with those chemicals anymore for a brief moment. And so the action potential only moves to areas where that chemical gradient is established the proper way. The environment is established properly. More sodium outside, more potassium on the inside. And so that's why we only move in one direction forward. The speed of the action potential as it moves along the axon depends greatly on what nerve it is. It goes from a few meters per second, like an autonomic nerve, for example, to about 120 meters per second. A meter is about 3 feet, so that's a lot. Right? That's 360 feet in 1 second. That's really a lot. The speed of those transmissions depends on a couple of things. It depends on the diameter of the neuron, of the axon. The bigger the diameter, the faster the speed, the smaller the diameter, the slower the speed. And then it also depends on the insulating myelin. Myelin is a fatty phospholipid, and it envelopes the axon. It makes a little fat wrapping around the axon, which means ions can't go through it. There's more fat. There's more insulation. So what we do, we have areas of those fat layers, and then we have areas, little spaces where there is no fat layer. Those are known as nodes of Ranvier. And so now the action potential cannot happen all along where there is this envelope, but it can only happen at the nodes of Ranvier, and so the action potential will jump from node to node to node to node, and that will enhance the speed greatly. It doesn't have to trickle down, little at a time. And so that's known as saltatory conduction. Myelin is produced by the glial cells, and those are the Schwann cells, when we look at the different nerve supporting cells. All right, well, hopefully you understand that. It's not an easy piece to understand, but I'm very happy to answer some questions as soon as we're in class.